No, that was for the last class.
Oh, I don't remember that.
You weren't special then.
Sorry.
Did I earn the cool little toy thing?
Nope.
No, we
All right. So, as promised, today we're going to talk about how might we teach a computer how to do sound. So, remember, everything that you ask a computer to do has to ultimately be distilled down to either the simplest of a math problem, in other words, 2 plus 2, or a very simple logical decision, true or false. Okay. So how do we take something as complicated as sound and turn it into something that simple? Well, to do this, we have to kind of go back and understand what the basic physical properties are of sound. So here is our classic graph of air pressure amplitude. Okay, and as we know, this is not actually what sound does in real life. It does not move up and down, right? It pushes and pulls at you. Okay, but what we're graphing here is pressure. So as we go up on the graph, that's when the air molecules compress together. When we go down, they're spreading apart. Okay, we already abstract this electronically. We've been doing that for many, many years in the analog world. What we're doing is like we have a microphone as this diaphragm, and as the air molecules compress, that diaphragm gets pushed on, and as the air molecules expand, that diaphragm gets pulled on, and that's sitting inside of an electromagnet. Okay, and that magnet creates an electrical pattern, right? Voltage going up, voltage going down, voltage going up, voltage. Okay, alternating current. Okay. So we have this voltage wave that represents that change of air pressure amplitude. We've been doing that for a long time. So that's where we began when we first started figuring out how might we get a computer to do this. We said, well, all right, we already know how to essentially transduce. Microphones are transducer, converting one form of energy to another. We already know how to transduce sound into a voltage wave, and it's relatively simple to have a computer read voltage, right? Because it's an electrical device, so it would be simple for us to create an input device that it would read voltage because it's already doing that. Okay, so that's ultimately what a sound card is. So an audio interface for a computer is really just a thing that allows a computer to read a voltage signal, an incoming voltage signal. Okay. So to do that, it has to take that voltage signal and convert it into something numerical. Right? Because really, although the computer could read voltage, right? You could relatively easily design an electrical device that would allow a computer to read that. Ultimately, if it was going to do anything with that information, it has to be a number now. Okay? So what we do is we have to sample this voltage. So we set up this clock, okay? And this clock at a predefined interval records the voltage, whatever that value is, and assigns that voltage a number. It says, okay, right now at this point in time, the voltage is this number. And then a little bit later, we check it again. And we say, all right, next point in time, the voltage is this value. So that's what's happening here with the dots. So each of these little blue dots is called a sample. So these are different points in time at which we sampled the voltage. And we have this scale. We've created a scale on this range where there's a number. This could be, just to make this very simple, we could say this is 0 to 10. Okay, it's much bigger numbers than that, but for now, let's just say it's 0 to 10. So between 0 and 10, where is the voltage at any given point in time? Okay, and so it just creates this never-ending stream of numbers as it's constantly sampling that voltage. And at that point, now your computer could do work on this. Now it's numbers, right? But great, I've got a whole list of numbers. I love numbers. And it'll back all that whole list will get queued up in RAM. And then you can say, all right, if you wanted to, for example, run a process that would change the amplitude or the gain of this sound, you would say, all right, I've got all these numbers lined up. Every one that comes through, add a 1 to it. And the computer just, great, send them on. And every number that comes through it, add a 1 to it. It comes out one value higher amplitude than it was when it started. Okay? The computer quite happily do that. Loves to do that kind of stuff. Okay. So that's the sampling piece of it. Okay. Now we need to talk about what we call quantization. I lose my thingy here. Let's see. Yeah, my ink thing doesn't show up there. All right, so quantization is all about, well, what happens if the value of the voltage doesn't line up with one of the numbers the computer knows? Okay, so if we're saying that this is 0 to 10, and we're only dealing in integers, well, what if the voltage lands between the value that we would assign 4 or 5? What if it's like 4.5? Well, the computer, you can't do that. It only knows how to do integers 0 through 10. So it has to do this thing called quantizing. And quantizing is where it basically assigns that voltage value to whatever is the closest number that it knows how to count. And so I've just given this scale. The red lines represent the voltage values that the computer knows how to record. And it's so far they're able to line up. Okay. So this is just talking a little bit about frequency. That, you know, here's 1,000 hertz, and here's 500 hertz. And you can see that between the different frequencies, you know, those fluctuations of compression or refraction are packed more tightly together with a higher frequency. And what we're trying to get at here is it's going to take you more samples to capture a higher frequency, okay? Because there's more fluctuations. If you wanted to accurately represent that digitally with numbers, you're going to need to sample it more often because there's greater fluctuations going on, okay? So let's take a look at how this works. Here's just a little animation of we've got our air pressure amplitude that's happening, and that's hitting the microphone. The microphone generates a voltage wave, and then this little blue little punch tool is essentially sampling it and assigning a number. Okay, so what gets fed into the computer is this stream of blue dots that represent some sort of number that corresponds to the voltage that came in. Okay, so this is what's going on inside your sound card. It has this little circuit called an analog to digital converter, or an A to D. And that's what it's doing. It's taking voltage and assigning numerical values to it at a predefined interval. That interval, by the way, is called the sampling rate, the rate at which we will sample. And it's measured in hertz, how many times per second. How many times per second do we check to see what the voltage is? Higher sampling rate means we check more often and therefore have more data. And then you got to do something with that data. The more data you have, the more space you got to have to store it, the faster the CPU you have to process it, so on and so forth. So you're always trying to strike this balance between how much data do I need to accurately capture and then process the audio faithfully versus at what point am I capturing more data than I need and causing myself headaches because I'm making my computer work harder and I need a bigger hard drive and more RAM and all that kind of stuff. Okay? Questions so far?
So it's just going to be a subjective evaluation of how much.
No, it's not actually. So there are some rules to this, and there's a thing called, and I don't know if I got this in here or not. It's called, yeah, here we go. So the next, you don't have to read all this, but it's called the Nyquist theorem. So there's this guy by the last name of Nyquist who came up. Scientists love to name, the laws after themselves when they think of them. When they think of something that makes sense, they say, "Well, we're going to call this after me," and then for the next million years, everyone's going to be saying my name every time they talk about this because I'm such a smart person. So anyway, so there's this guy named Nyquist, and he came up with this idea of sampling rates. And what he observed was that if you want to, given a certain frequency, if you would like to sample that frequency accurately, your sampling rate needs to be at least twice the frequency of the sound. So if you want to sample 1,000 hertz, you have to sample that at a rate of 2,000 hertz. right? And if you do, then you can get it. It'll work. That's all you need. You only need twice as a sampling rate. You need to sample twice the frequency of the sound you're trying to get. So let's take a look at how this works. So here's a sound, or a little sine wave. Here's a 637 hertz wave for some reason. All right. So if we were to sample this at 500 hertz sampling rate, this is where the samples would fall in. Okay. So 500 times a second, it's taking a picture of the voltage. But this happens to be a 637 hertz wave. So we're actually sampling at a rate that's lower than the frequency. So what's that going to do when we ask the computer to rebuild this wave? Because on the way out, if we want to hear what the computer did to it, we have to convert it back to analog. So there's another device on your sound card called the D to A, which does the inverse, right? So it takes some digital number and creates a voltage value out of that and sends that out your headphone output or whatever. Okay? So when that happens, what's the computer going to do if this is how it was sampled? Well, when it tries to string those samples back together again, it's going to create that red wave. All right? Because it's going to try to connect these dots. And we didn't have enough dots to accurately record the pattern of that wave. So this is called aliasing. So if your sampling rate is too low, you end up with this alias. And this computer will spit out a frequency that's lower than the one you started with.
Yeah, that's going to be 2 octaves lower, right? Than the original.
Yeah, probably about, yeah. So it's going to be quite a bit lower. And that's a real bummer. You would not be real happy with your computer if that's what it spit back at you, given what you sent in. So we would like to avoid this. The way we avoid this is by making sure that we are sampling at least twice the sampling rate. That's twice the frequency, okay? So let's take a look at how we might do that. Okay, here's just a graph. So this is the one that we just did. Okay, 637 hertz as compared to a sampling rate of 500 hertz. This is how it's going to be drawn. Right, the black wave is what you started with. The red wave is what you end up with digitally. All right, so let's do another one. Let's take this. Let's drop it down to 600 hertz, and let's do the Nyquist theorem on this. And we'll say 1200 hertz. Okay, is what we would need to sample that. This won't alias. Okay, because we're sampling it. The one slight thing I don't like about the way this animation turned out is that it's not entirely intuitive what's happening. But in reality, the reason why the Nyquist theorem works is that you would ideally be sampling here. Right? And at that point, that's enough information to do it. Okay, so I don't quite like this animation because of that, but that's the way that it turned out. Let me just take it up to 1300 hertz, sample it, and now you can start seeing how this would work. It says that this frequency is not going to alias either. So as long as you have you're sampling at a rate of twice the frequency, you'll get it. And, I could keep going up here. I mean, I could take this up to 2000 hertz sampling rate. And I get no better wave in the end. All right, I'm getting the exact same wave out regardless of the sampling rate.
You would, though, if you had something other than a sine wave, though, right?
Well, so something other than a sine wave would actually represent more frequencies, right? So you have more than one frequency going on. So, but yes, if 600 hertz is the only frequency I care about, then yeah, the bare minimum, I just need 1200 hertz sampling rate and I'd be fine. But yeah, in a complex sound, you could have lots of frequencies going on at one time. And so you want to make sure that your sampling rate will accommodate whatever is the highest frequency. Because we know in order to accurately capture any given frequency, we got to sample at twice that rate. That's all you need. You don't need any more than that. As I've gone up to 2000 hertz, I get the exact same wave out of it. Okay? So if this was the only frequency I cared about, I'd be wasting data and CPU cycles and all kinds of things sampling at that rate, because I don't need it. So how do we know if we were to kind of generate some sort of catch-all sampling rate that would capture all the sounds we care about, what would that be? Well, what's, on average, the highest frequency that a human being can hear? about 20,000 hertz. The books tell you. In reality, it's more like 16,
Yeah.
right? And the older you get, that drops lower and lower and lower. You know, David Smith, for example, he'll tell you that the highest frequency he can hear these days is like 10K.
Me too.
Yeah. So as you get older, particularly sound people, this is like one of these occupational hazards for us. Is if we're not careful, we expose ourselves to more noise than we should, and that accelerates that hearing loss. So you know, as you just get ready. I mean, you certainly need to wear earplugs as often as you can, but be prepared that as you get forward and longer in your career, that your ability to hear these frequencies is going to drop. But yes, I mean, let's say that we believe the textbooks, and you know, on average, a human being can hear 20,000 hertz, right? So what would be, if that was the highest frequency that any reasonable person ought to be expected to hear, then what would be a sampling rate we could use that would make sure that we caught all of those frequencies they could hear? What's that? 40,000. Yeah, so let's put that in. 20,000 hertz. Oh, it won't let me do that. Let's pretend that's 20,000. And then if we did 40,000, then that would not alias, right? We would get that frequency. That would be fine. Okay. So yeah, it doesn't like it because it wants 100 to 1500. But I gotta talk to the programmers who made this for me. This is where some of these standard sampling rates come from. So the standard sampling rate for CDs, compact discs, which is a digital storage format for audio. Anybody know what the standard sampling rate for that is? No. 44,100 hertz.
Yeah.
Okay, 44.1 kilohertz. Well, why is it more than 40? I just got done telling you don't need more than 40. Well, here's why. So inside that converter that does these digital to analog and analog to digital converters, one of the ways we avoid aliasing is we make sure that we never feed a frequency into that converter that is not capturable by that sampling rate. So if we say that, you know, we're sampling at 40,000 hertz, okay, then the computer is going to know that the highest frequency we're reasonably going to be able to sample is 20,000 hertz. So ideally, it's going to want to make sure that any frequency higher than 20,000 hertz never gets fed through the converter, because it'll alias if it does. Okay, it'll end up being interpreted as lower frequency. So there's always a filter. It's a low-pass filter, EQ filter, that gets applied to that voltage signal before it goes through the digital converter. Okay, so there's this low-pass filter that's set at the cutoff frequency of whatever your highest frequency you can sample is. Well, has anybody ever seen a low-pass filter that is this like brick wall that doesn't let anything through after that cutoff frequency? Because I never have. If you were to graph any sort of low-pass filter, okay, and you have, you know, frequency on this side, amplitude on that side, so this is hertz, this is dB, you know, a low-pass filter is going to look like this, right? And your cutoff frequency is going to be there. So the cutoff frequency is usually the point at which the filter is dropping 6 dB. So this is minus 6 dB. And then it starts aggressively attenuating frequencies above that. But it's not until you get quite a bit higher that it finally goes down. And this is called the filter order. It's how many dB per octave. It's like, you know, you get first order filter, second order filter, third, if you've ever heard that. You can dial that in on a crossover, for example, when you do a filter. So what I'm getting at is, just because you set that low-pass filter to 20,000 hertz doesn't mean nothing above 20,000 hertz is going to get through. Even the most aggressive low-pass filter in the world, a fourth-order 48 dB per octave filter, is going to let a few things through that are higher than 20,000 hertz. Okay, so this is why we want a slightly higher sampling rate. So 44.1 kilohertz was designed. That was chosen specifically to accommodate the type of low-pass filter that they thought they could reasonably expect every electronics manufacturer to afford. Okay, so at the consumer level. So 44.1 kilohertz is the consumer standard for sampling rate.
I don't understand the issue. If why build that buffer in 44.1 if you have a frequency that's higher than 20 hertz we can't hear anyways, and it aliases down to a frequency that we can hear?
Yes.
What's the problem?
Because you don't want to hear. So you've got this frequency that you can't hear that suddenly turns into this frequency you can hear that's different. That's what you don't want. You don't want this 22 kilohertz that you can't hear to suddenly find its way into your sound masquerading as 800 hertz, for example.
So you can. So when they, I guess, recorded the music, you're recording music at higher frequencies than you can hear, I guess.
Sure. Yeah. I mean, that microphone can pick up all kinds of stuff. Just because you can't hear it doesn't mean it's not happening.
Yeah.
Okay. So yeah, there are all kinds of sounds happening that we can't hear, but they're happening, and there are microphones that can capture them. Even cheap microphones can capture them to some extent. So that's what we're trying to do. So they said, well, it's really about how fancy of a filter can you afford. And for consumer-grade equipment that we're going to sell to mere mortals at Best Buy, if we say 44.1 kilohertz, then that corresponds to a certain type of low-pass filter circuit that was inexpensive enough that they thought, well, that would not break the bank for consumer-level equipment. Okay. However, consumer level or professional level stuff is 48 kilohertz. That's the standard sampling for professional stuff. So there were two different sorts of storage formats for a while there. There was compact disc and there was DAT, digital audio tape. Okay, and the DAT was what professionals used. And they said 48 kilohertz because the professionals sort of didn't like how aggressive that filter was, because that's doing all kinds of phase modifications at the highest frequencies where all your transients are, because that's the way a filter works, is it starts manipulating the phase. Okay? So they're saying, well, if the filter's that aggressive, it's going to be doing all this crazy phase stuff at 16 to 20K. We sort of don't want that, so we would like a slightly less aggressive, more sophisticated filter, and therefore we need a slightly higher sampling rate to accommodate those extra frequencies that are going to be let through. So that's why 48 kilohertz is the professional standard. Okay, and so for pretty much everything you do, that either 44.1 or 48, I tend to stick to 48. You just got to pick one and go with it. Should be fine. You should be able to capture everything that you can hear. Okay? So why do they make things that sample at higher, at like 96 kilohertz or 192 kilohertz or something? There are a few schools of thought there. I mean, first of all, you need to know that the science is true. Okay? I mean, this Nyquist theorem is true. It's been proven true over and over and over and over again. It's not made up. Like, that's real. So, I mean, those extra sampling rates don't actually have any impact on making the sounds that you can hear sound better. 96 kilohertz doesn't make 100 hertz sound any better than 48 kilohertz does. Okay? All a higher sampling rate will do is allow you to sample higher frequencies. That's all it does. Nothing more mystical than that. It just allows you to sample higher frequencies. Why would you want to do that? Well, maybe you're like super hyper concerned about stuff and all these sounds that you can't hear, and that you think that maybe they have something to do with the stuff you can hear, and they do. There's an argument that says that although I can't hear these really high frequencies, they are interacting with the frequencies I can hear, right? And we know that that happens. We know that two sound waves can interact with each other in destructive and constructive ways. That's what causes cone filtering. So you could have some harmonic interval of a frequency that I can hear, some harmonic that's like 3 octaves up that I can't hear at all. And it's absolutely crafting how I perceive the frequency I can hear. Okay? And so if I were to remove that high frequency out of the picture, even though I can't hear it, it would have some impact on the frequency I can hear. It will change the tone of that instrument, for example. So what makes a clarinet sound like a clarinet is all of the harmonics, right? So there's all these harmonics that go on forever. Okay? Well, what if I get rid of all the harmonics above 20 kilohertz? Does it still sound like a clarinet? Yeah, it still sounds like a clarinet. But if you really love clarinets and they're like your thing, and you've got, you spent $1 million on your clarinet, and you know exactly how it sounds, you might actually feel like you hear the difference. Notice I say feel like you hear the difference.
Yeah.
You may or may not actually hear the difference, but you will believe that you do. And so this is where the higher sampling rates come into play. It just allows you to sample higher frequencies. That's all it does. But you only get that benefit if every element in your system is capable of processing that frequency. So do you have a mic? So let's say that you really care a whole lot about 40 kilohertz, like that frequency that you can't actually hear, but you care a whole lot about it, and you want to make sure that you can capture it. So you're going to want to sample at least 80 kilohertz, right? So that's where the 96K comes from. So you're going to get your 96 kilohertz sampling rate, and that gets you the ability to sample 40 kilohertz. Great. Do you have a microphone that can pick up 40 kilohertz at the same amplitude that it can pick up everything else?
Does that exist?
Yeah, they're expensive. We have a few of them in our shop, and they cost us about $1,500 a pop. And they can sample 40 kilohertz.
Like which one?
The Sennheiser MKH8040s, those little Sennheiser ones that the detachable caps and everything that we use for the floor mics in South Pacific that we never turned on. Those can sample those can capture 40 kilohertz, at relatively the same amplitude as everything else. So you got to have that, right? So you got to have a microphone that can you've got to have a sound that's actually making that frequency first. Then you got to have a microphone capable of capturing it and turning it into a voltage wave. Then you have to have some sort of converter, right, and a preamplifier that is able to amplify that without destroying it, and then run it into a converter that has a filter that's not going to filter it out, right? So whatever the filter is that's in your analog to digital converter has to be a filter that isn't going to filter out 40 kilohertz.
Can we also have a visual display so that we can see the 40 kilohertz being recorded?
Yeah, so you're absolutely sure that it's
so you're
happening.
sure there is,
Right, so you have to have that. The filter can't be filtering it out. The converter has to be capable of running the clock that fast, right? Because you've got to run the clock at 96 kilohertz, great? So you've got to be able to do that. You've got to have the RAM to store twice as much data and buffer it. You've got to have a hard drive capable of now storing, because that same recording is going to be twice as big now in data. You've got to have a CPU fast enough to crunch twice as many numbers at the same amount of time. And then you have to actually, let's assume you could do all of that. Let's assume you could capture all of that. It's great, it's perfect. You mixed it in Pro Tools, Logic, or whatever. It's great. Now you want to actually play it for something, this pristine thing that you've now recorded. Okay, now you have to have a digital to analog converter that can do everything backwards that you just did before. So it has to be a nice enough converter that can run at that same sampling rate. So you have to actually play it back at that same sampling rate, and then the converter is running that fast. Okay, and then it's creating a voltage wave that actually represents 40 kilohertz. Then you have to put it through a power amplifier that is able to amplify that high of a frequency without destroying it. That's tough to find. And then you got to have a loudspeaker capable of reproducing 40,000 hertz in the air.
That's impossible. I'm there.
Somebody call
I
me
mean, there are really expensive audiophile, hi-fi companies that claim to be able to make this stuff.
Really?
What is the gain? You can't hear it.
Can I claim that I can? Because it's not like you can prove it.
Well, that's the problem. It's really tough to prove that it's happening. I mean, you can develop the circuits and everything, but what's really tough to prove is can you hear it? And it just turns out it boils down to subjectivity. So I will tell you, I have a colleague of mine who works in this area. He makes cables. So his job is he makes cables that can do this. Loudspeaker cables and line level cables and everything that can handle this kind of fidelity. And he sells them for insane amounts of money to people. And I've been to his place a few times, and I've listened. He's got supposedly all of the components that do all of this. And I have to say, it sounds amazing. I can hear something. It sounds amazing, but is it amazing enough to spend all that money and all that time and all those components to do that? Not for me, it's not, but for some people it is. But that's all that gets you, okay, is the ability to sample higher frequencies. It does.
So just make would it theoretically just make the frequencies that you can hear have more clarity?
No.
But would it? Because if you can't sample at that high rate, it would alias everything down. It would muddy the frequencies that you're
Well,
getting.
that's the theory. Is that
So there's more
but
clarity.
really it doesn't, because remember the converter filters out the frequencies so they don't alias.
Where
Right.
in the process is that converted?
In your audio interface, your sound card. So your sound card has a filter that filters out all the frequencies that can't be sampled. So we don't aliasing doesn't happen anymore. It's this, it's an interesting sort of, academic exercise to say, hey, look, this is theoretically possible, but really every sound card and converter you have has a filter in it that stops it from happening. So you set the frequency.
But then you're changing phase or modifying phase, right?
Well, every time you apply an EQ, you're doing that.
Right.
So it's just
So this is just doing it without any of the phase change, without any of the aliasing, without any of that. You can just hear. It's like leaving the higher frequencies really pristine.
it lets you sample higher frequencies. That's all it is. And these phase changes I'm telling you about are minimal. I mean, it's not. Most people can't hear them. So right. This is what I'm getting at. Is we're talking about. Yes, the science is true that yes, higher sampling rates can sample higher frequencies. But I'm saying, what does that gain? Very little in reality, because really aliasing doesn't happen, except in very bizarre situations. I found one actually that was happening with QLab for many years, but usually it doesn't happen really anymore. So that higher sampling rate doesn't get any better sound for the stuff you can hear, right? The frequencies that you can hear aren't changed. All that does change, potentially, is some of those higher frequencies, and nobody's been able to prove this yet, but the theory makes sense to me, that those higher frequencies, although you can't hear them, they do impact the way you perceive the frequencies you can hear. Those frequencies aren't being changed. What is being changed is the way you perceive them. And that perception is impacted by these frequencies you can't hear. That's the theory. Yet to have somebody show me that empirically and I can prove it. I haven't, but that makes sense to me.
Are they saying that perception? Are they saying anything about that perception, like what it's doing?
Well, if, again, it has, in order for you to know and hear that, you have to have some point of reference. So in order to appreciate whatever change that is, whatever difference that is, you have to have something to compare it to. So going back to the $1 million clarinet, if you have this $1 million clarinet and you've spent your whole life listening to that $1 million clarinet in real life in a real room, and you know what it sounds like, then yeah, maybe you could hear the difference when that's digitized. Maybe, probably could actually.
This is probably a very subjective statement, but I think I've experienced that. But I experienced it in terms of sight.
Mm-hmm.
I was in some major recording studios like Sound Lab and in New York City, and when I go into their studio, it just seems like my eyesight is clear for some reason.
Yeah, I mean,
I don't know if it's their sound. I think it's their sound is producing it, but I don't hear anything different. It just seems.
Yeah, I don't know. I will say I've been in situations where I have felt as though I'm hearing a difference with these higher sampling rates. I can't pinpoint exactly what the difference is, but it's very, very subtle. Here's the interesting little bit of information, though. This is what fascinates me about this. So the recording industry, this was now 15 years ago or something, when the MP3 issue was rearing its head and the recording industry was trying to figure out what to do about it. They started doing, as much as they were fighting it, they were also trying to figure out what to do with it. And they were doing a lot of research. There was a couple of research labs out in California, and I know one of the guys that was working with them. And they did one experiment where they made recordings of something, more than one different recording, recorded it at multiple sampling rates, the same performance. And they played those different recordings to listeners, just normal people, and most people could not hear the difference. They said all of those recordings sounded the same to them, and they were just the only difference was the sampling rate. But then what they did is they took all of those separate recordings that were all at different sampling rates, and they converted them all to the same format of MP3. So the exact same 128 kilobits, whatever, MP3. And those average people could actually hear the difference between those MP3s. So the MP3s that were created from the 192 kilohertz recording sounded different to even an average person. It sounded different to than the MP3 that was created from the 44.1 kilohertz recording. Nobody really knows why. Why is that? I don't know. But they were able to repeat it, and sure enough, over and over, people could hear the difference. And so that's the real reason why there's this big push for these higher sampling recordings in the recording world, is ultimately they're saying, yeah, it really doesn't have a huge impact on what people hear off the CD, but it has a big impact on what people hear on the MP3 that they buy off Amazon. And that MP3 sounds better if we record it at a higher sampling rate, but the CD sounds no different. So that's interesting to me.
Did you say MP3s were just throwing away bits or something? Like
Yeah, that's why nobody can quite make sense out of it, because what you're doing with an MP3 is it's this algorithm that attempts to figure out, of all of the things we're hearing here, what is superfluous? What do we not need in order to perceive what this thing is? So if you think of the clarinet again, how many of those harmonics of the clarinet do you really need to hear in order for you to know that it's a clarinet? The idea is you've heard clarinets before, you know what they sound like, and if they had just a little bit of that harmonic pattern intact, your brain would fill in the rest because it recognizes that pattern. Okay, so you have this vocabulary of what in your mind of what things sound like. And if you hear something that is close enough, it's enough of that pattern that you recognize the pattern, then your brain will say, oh, that's the clarinet. And you actually hear in your mind what it would have sounded like without all of that compression. That's the theory behind MP3.
But what happens in between all these bits that you're sampling? So like on that chart right there, that line that's connecting two of the dots, what is that in between them? Is there like a, you know what I mean?
Well, so what happens is it's called a smoothing filter. So once the converter takes that data and converts it back to analog, if really the way it would, if you were to draw it the way the computer would draw it, it would be like this. Right? This would be the wave as far as the computer was concerned. Okay? So what happens is then there's this analog filter that takes that and smooths that out, and that's how you get the actual wave. Okay? That's all that's happening. In the MP3, we're talking about not sine waves. We're talking about the MP3 algorithm looks at it as a complex tone. So it looks at all of the frequencies together, and it tries to figure out patterns there. And it tries to see, okay, I can see a harmonic pattern. To what extent could I degrade that harmonic pattern? In other words, not have to store some of that information, but leave enough of that pattern intact that the human brain will recognize it and perceive it as the full thing. So here's where it gets really bizarre to me, is this whole theory relies on the fact that you have this vocabulary of sound in your mind of things you've heard before. Right? So you've heard the pattern before, and therefore when you hear bits of the pattern, your brain fills it in. But now we've got a generation of people that all they've ever listened to are those MP3 recordings that don't have the full pattern. Never been to a live concert. They've never listened to a CD. All they've ever listened to is the stuff they've got off iTunes.
Maybe that's why the higher sampling rates sound better compared to an MP3, because it's actual recorded sound instead of relying on the perceived sound. Because there is no bank for them to perceive. Let's say a person hasn't ever heard a kick drum in their life.
Well, no, because there's another study they did where they took young people, these people who have never heard a whole lot of full resolution, and they played the full resolution and the MP3 for them, and they prefer the MP3.
Really?
Yeah. They say, I prefer that. That sounds better to me. And
Well, I guess they're used to it.
well, that's the interesting thing to me is this whole idea of these MP3 and MP4 and all these compression algorithms rely on this fact that you have this vocabulary already, the things you've heard, that you fill in. What if you don't have that vocabulary? What are you hearing? And so there's a part of me that feels like there's a generation of people now that have a completely different sonic vocabulary than the previous generation. And so what they're hearing in that MP3 is something very different from what I'm hearing. And that's why they prefer it, because it sounds very different to them. It's a pattern thing. It's that they don't, to them, they can hear the difference because the compression is not creating this thing that their brain fills in the gaps of. Okay? Like their brain processes it differently than mine does. And that's really interesting to me. I don't quite know what to make of that yet. But as a sound designer, as someone who's trying to figure out how to deliver content to people, that worries me a lot to think that they're hearing it in a very different way than I'm hearing it. And if I'm supposed to be creating it in a way that sounds right to me, but what my audience ends up hearing is something quite different, I don't know what to do about that. So, I don't know. That's just sort of like Jason Romney's musings, things that I think about sometimes. Yeah.
Getting back to that smoothing filter,
Yeah.
is that audible? I mean, is that a good reason why you want the highest sampling rate your computer can actually do, so it'll reduce the amount of filtering? Filter will do?
The scientists tell me no. I mean, they say that the smoothing filter will fix it. So there are certainly better and worse smoothing filters out there. And that's where, so you can spend more money on your converter and get a better smoothing filter. But no, the sampling rate itself doesn't seem to have an impact on the smoothing filter's ability to do its job. But there are certainly cheap smoothing filters.
Well, if you have more bits, that's less smoothing in between two bits, right?
Well, I mean, sort of. But the point is, in some ways, the difference between smoothing and not smoothing is, I mean, if you think about the loudspeaker that would then have to reproduce that, I mean, it's still moving, right? Even if it's stopping here and there. It's a good way to burn up your loudspeaker, but it would still be making the wave, right? Ultimately, that pressure wave would still be intact. So, I think that's really just, the smoothing filter is just the icing on the cake, right? It's not a huge, massive difference in what we hear, but it's enough that they want to do it. It makes enough of a difference that we care. But no, it's the higher sampling rate. It's not really going to help that. All right, and science of that has been proven over and over and over again. That whole notion of the Sniper's theorem. Okay, we need to talk about quantization. All right, well, yeah, great. I don't need those questions. So let's talk about that. Because that's the other side of this. We talked about sampling all this time, and I mentioned quantization briefly. But let's take a look at what that really means. All right, so here is our sound and this wave that takes forever to draw. I don't remember if something happens when it's done or not. No, it doesn't. Okay. So, let's take a look at what quantization really does. So there's this notion of bit depth. And bit depth is the number of voltage values we can assign digital numbers to. Okay, so it's that range here. So if we say a bit depth of 2, and we'll learn when we learn binary what that means, but a bit depth of 2, how many possible combinations are there with 2 bits? Anybody know?
1 and 0.
Yeah, so if you have 2 of those, how many possible combinations of 1 and 0 could you have? 4. Right, okay. So you're talking about potentially 4 different voltage values. Okay, so if we put in a bit depth of 2, this is what happens. This is assuming we have a sufficient sampling rate. Okay, so basically, we only have 4 values we can do. Anything that goes past this top one just gets truncated. All right. This is going to have an impact on how loud something sounds. Right. It's going to have an impact on the different volume levels that we perceive. Okay.
Why is 1 above and 3 below?
Because the computer counts it from the bottom up. So for the computer, from the computer's point of view, it starts here at 0 and then goes up until it runs out of numbers. That's just how the computer does it.
Let's set that interval then. I guess. Like why?
Well, yeah, I mean, you could, depending on how the digital converter is configured, you could say that you could basically say that my 4 is going to be all the way up here, and then the spacing is going to be bigger. You could program your design the circuit that way. Right. This is just one example. I wouldn't read this. It's just a flash animation. I would not read too much into it. But if I go up to a higher bit depth, so now I've got a bit depth of 5. Well, you know, how many combinations do I have with 5 bits? Yeah, so got more. So now I'm able to get a much finer level of detail on the amplitude spectrum. Okay, same sampling rate, but greater resolution for amplitude. Okay. So, and this is, you know, just allowing you to go even higher. So here's a bit depth of 6, pretty good. You still can see it's a little jagged, right? And I can take it all the way up to 16, and you know that. I mean, we're getting all the way up to the peak for sure at that point. Okay. So that's what bit depth's all about. And let's just get a sense of what this stuff sounds like. So this is, so very simple, right? 8 bits and 4 bits. So as the bit depth goes down, essentially your noise floor comes up. And this is what's called quantization error. So every time it has to approximate a value, it throws out a bit of noise as a result. Okay? So every time the voltage value that's coming into the converter, every time that voltage doesn't quite line up to one of the numbers it can do, it has to bump it up or bump it down to whichever's closest. And that process of bumping it up or bumping it down spits out a bit of noise, called quantization noise. So the more times you're quantizing, and quantizing is this process of slotting it into the closest thing. Every time the more quantizing you do, the more spurious noise is being generated as a result. So you get noisier stuff.
So if you have a higher sample rate, you'll have to quantize less, so you'll have a less noisy file.
No. So quantizing, you know, bit depth and quantizing is a totally separate issue from sampling rate. Sampling rate is all about frequency. Okay. Bit depth is all about amplitude. Okay, and ultimately dynamic range, because the higher the bit depth, the greater dynamic range you have. In other words, the greater difference between loud things and quiet things you can capture before you hit noise. Okay?
That makes sense. My question is, so quantization is a process that happens in regards to sample and bit depth.
Right, so every time you sample, you are assigning a numerical value to a given voltage. Okay? So what bit depth gives you is how big of a number is that sample? So for every time I sample, am I dealing with a number that is 2 bits long, or 16 bits long, or 24 bits long? How big is that number? What are the possible values I could assign that voltage for a given sample? So if you go from 8 bits to 16 bits, each sample is going to be twice as big. Right?
Are you defining, what are you defining right now? Or defining exactly?
Bit depth.
Okay.
So for each time you sample the voltage, how big of a number are you able to work with? Each sample could be, you know, a range of, if it's 16 bits, it could be a range of 0 to 65,535. All right? Yeah. Okay. 5 if you count the 0.
Sorry, forgot the phone.
Which is what computers do. Okay. So that 65,535 is the total. That is the number of different voltage values you could assign. Okay. Whereas if you only went to 8 bits.
What is this math that you guys are doing?
Just doing it.
We'll learn it later. 256.
Yeah.
Oh,
So
I was getting there.
256 different values at 8 bits. Okay, so all of those values that used to fall in somewhere in that 0 to 65,525 scale, a lot of them are going to fall in between the values on the 8-bit scale.
What is quantization a process?
Yes. It is the process of assigning a numerical value to a voltage that doesn't fit within the numerical scale. So it's a voltage that's somewhere between 4 and 5.
So that's so quantization error is just the noise because of that.
Yep.
But it's not the process of reassigning.
No.
Okay.
So the noise is the byproduct. Just like, you know, a loudspeaker does generate some sound and it also generates some heat. The heat is the byproduct. So noise is the byproduct of quantization.
Okay, so I guess my final question is the goal to just make the computer have to quantize fewer times?
Yes.
Okay, solid.
Let me show you. All right. So
What happens if you didn't quantize?
you have to.
What if you did?
You can't not do it. You could listen, because what you've written a program that tells the computer, hey, look at the voltage coming in. Assign a number to it every time you look at it.
What if you assign it in a way? Okay, yeah.
The computer's just going to do what it's told. It's going to assign a number to it. And it's just going to pick the closest number it can find.
And if it didn't, if it just dropped up those numbers that weren't exact, you would just have to say.
Right. So you could write a second line of code that said, hey, computer, sample all the voltage values at this defined interval. And if it's a value that you can't assign a number to, just throw it away. You could do that.
So it either quantizes or throws it away.
Right. And you don't want it to throw it away,
Because then you have less sound.
right? You would much rather go ahead and quantize it. And you get a little bit of noise, but you get the sound too. Right? So you have to quantize it. So let's take a look at what this looks like and sounds like. So I'm going to listen to the quantized signal. This is just a sine wave. And I'm now at 16 bits. Now I'm going to take it down to 4 bits. Okay? So what's happening here? So the green wave is the source. The red wave is the digital. Let's see if I can, there we go. So the red wave is the digital version, and the yellow wave is the noise that was a result of those quantization errors. And the thing to note is that what happens when really aggressive quantization is happening, it's more than one kind of noise. There's some hiss that happens, but there's also some distortion that happens. Okay, and you notice that we're getting now all of this harmonic distortion.
Yeah, I can hear a pitch. I can
Yeah.
hear a fifth above.
Right, yeah, because it's creating harmonics as a result of that, which is also kind of a bummer. Okay, so and if I go all the way down to 1 bit, so 1 bit now, I only have 2 possible values I can assign for this voltage, 0 or 1. So that's what you're seeing here on the red wave. It's either 0 or it's 1. Okay? And as a result, it's creating all kinds of extra noise. All right? A whole bunch of hiss and a ton of harmonics. Okay? And so if I take the bit depth back up, eventually I get to a point where the quantization noise is not enough for me to hear. One thing to notice here is this signal to quantization noise ratio, SQNR. That is the difference in amplitude between your sound and the noise that is spit out by the quantization error. How much difference in level? Right now, at 16 bits, that's 96 dB.
What is this called?
Signal to quantization noise ratio, SQNR. It falls into that category of signal to noise ratio that you deal with all the time. So what is the difference in level between the thing I'm listening for and the noise?
Signal to noise quantization level.
Signal to quantization noise ratio. the ratio between my sound and the noise. And right now that ratio is 96 dB, which means I hear my sound, and then 96 dB quieter than that is the noise. Well, that's quite a bit, okay? Right now, with the air going on in here and everything, I would say the noise floor of this room is probably about 60 decibel sound pressure level. And I'm playing this sound at about 70 decibels. So you're basically hitting the noise floor of the room 80 dB before you ever get to the noise of the quantization signal. Okay? So you're never going to hear it. So 96 dB is plenty of a ratio. Okay? But as I take this down, so if I go back down to 8 bits, now there's only 48 dB between my sound and the quantization noise. Still plenty for this room, right? And even if I turn this up, you would have a hard time hearing it. So there's the original signal. There's the quantized signal. You can't hear the noise, right? It's that the 48 dB is plenty. But as I start dropping it down, now it's 30 dB. Now I'm actually starting to be able to hear it. 36 dB, 30 dB, 24 dB. Now I'm hearing it, right? Okay, let's listen to what it sounds like with just music.
What did you change before you changed the bit depth to make it go from 96 to 48?
What I did is I just was toggling between the original sound and the quantized sound just to see if it was A being the difference, just to see if we could hear the difference between the two, and we couldn't. All right, so let's do this with actual music. So here's 16 bits, and you can see, so potentially we've got a 96 dB signal to quantization noise ratio here. But as you can see, it fluctuates depending on the content of the sound, right? So we're fluctuating here between, that 96 and around, in some cases, 70 or so. It just depends on, ultimately, the amplitude of the signal. So lower amplitude signal is going to drop that ratio, which is why you want to crank that preamp as high as you can when you're recording stuff. The higher you crank that preamp, the greater that signal to quantization noise ratio becomes, okay? Without clipping it, though. All right, here we go. Let's start dropping the bit depth. We didn't. So still fine. Remember when we started getting to 5 and 6, we started being able to hear it on the sine wave. Starting to hear the noise now. Okay, let me go back. There's the original. Here's the quantized. You hear that noise? I can isolate the noise. That's the noise we're creating as a result of this quantization. If I go back to 7, it's 8, 9, it's now dropped below the noise floor of the room. You can't hear it. Okay? So keep going down. I can capture this at it. Trying to capture it at a time I can see it. Oh, we can zoom it. So this is what's happening to our complex tone. All right, so the green is our source wave, the red is the quantized wave, and the yellow is the noise that gets generated as a result of it. Okay? And we can take it all the way down to 1 bit. Should be a super great way to blow our loudspeakers.
78s.
Yeah. Okay, lots of noise, right? But then we also get the distortion. This is the weird thing about quantization, is you get the hiss, but you also get the distortion, which is like, you can almost live with the noise, but it's the distortion that really kills you. And now, look at our signal to noise quantization noise ratio. It's only 6 dB. There's only 6 dB difference between our sound and the noise. That's not very good, right? Okay. So, isn't that a cool little demo? Eric Schwartz. Eric Schwartz, ladies and gentlemen, graduate of our program, made that for me.
I love how it gives you the option to pin every little photo on your website.
Yes, isn't that great?
Everything. Like even the little logos for like the modules. and
Right.
tutorials, it's like pin it, pin it, pin it.
This is part of the WordPress plugin I'm using. Okay. So why do we care about this? Well, just like you have to pick a sampling rate, you have to pick a bit depth. So what bit depth do you want?
Oh, the big one.
24, something high.
Something high would be great, right? Something, better than 5 or 6 or 8, Well, the hugest bit depth possible would mean that your samples are enormous.
Oh, that takes up a lot of space.
Yes.
Okay.
So it's a balance. What's the balance between the biggest number I can get and the biggest number I think is reasonable to expect my computer to store a gajillion of? 16 bits is usually plenty. As we've seen, 16 bits gives you a 96 dB signal-to-noise ratio. I don't know about you, I've never been in a listening environment that had a 96 dB noise floor, right? I've never been in that room. And I've been in an anechoic chamber.
How long were you able to stay?
How long were you there?
It gets a little on your nerves after a while.
Yeah.
But even that has some noise floor to it. I don't know that I've ever been in a room that had a 96 dB signal-to-noise ratio just as part of the actual listening room. So that ought to be enough. Okay, so if 16 bits ought to be plenty, then why in the world would you ever want to do 24 bits, which is usually what your other standard option is with most of your recording systems? Well, 24 bits gets you potentially, I believe it's 120 potential dB signal-to-noise ratio, I think is what it is. So why would you ever want to do that if 96 dB is enough? Well, no, this has nothing to do with clarinet player, actually. This has everything to do with lazy sound engineers. Okay? Because if you do it right, and you have your gain structure correct, and you're cranking those preamps as high as you can get them without clipping, and you're doing your due diligence on that, and that way everything that's coming in to your converter is coming in at the highest voltage it can, then guess what? Your noise is 96 dB quieter than that, and you won't hear it. But if you're lazy, and you don't take the time to really line up that gain structure really well, and maybe your voltage is coming in, 40 dB quieter than the highest voltage the computer could sample, well, guess what? Your noise is about 45 dB quieter now than your sound. So you've cut your signal-to-noise ratio almost in half, which would kind of stink, right? Because then if you now take that and try to mix it and EQ it and boost it up, you're going to mix it, gain it up because you've never did it originally. You're going to gain it up in the mix. Well, guess what happens? That noise comes up with it. Okay, and suddenly you got this noisy sounding recording. So, however, if you record at 24-bit, then you've got potentially 120 dB signal-to-noise ratio, which means if you're lazy and don't adjust your preamp, and maybe you've got that 40 dB of headroom above what you could be using that you're not, well, now your sound, your noise is now 70 dB quieter than your signal that you were too lazy to line up. Well, 70 that's workable, right? You can still work with that, right? You could then turn that up and you still wouldn't hear the noise. So that's where the 24 bits comes in handy. It's all about lazy sound engineers. Yeah.
Can I defend the lazy sound engineer?
Yeah, go for it.
Okay. With tape, reel-to-reel, you have some, you can overdrive the tape ever so slightly.
Oh, yeah.
And good. But if you do that in digital, it's
Oh, yeah.
It's the end. So, it's safer to have your preamp lower.
Exactly.
Once you do it, too much, that's it.
Exactly, and I've been in that scenario. I've done recordings where I've botched it and suddenly it clips, and there's no going back from that. I mean, you can't undo that, and then you got to get the musician to do it again, and sometimes they can't. I've been in that situation where I've botched a recording because it clipped, and I said you got to do it again, and they never were quite able to repeat that performance. and that stinks. So this is where the 24 bits can help you. Now this is all assuming you've got to have really good preamps that don't introduce any of their own noise into this scenario, because your preamp can introduce some noise long before you ever get to the point of quantization. So if you've got really quiet preamps and good 24-bit converters, then yeah, you can afford to be a little lazy with your gain structure, and it has negligible effects on anything. I mean, the only downside there is storage space, right? So you've got to be able to store bigger samples now. So more RAM, bigger hard drives, faster CPU is what you need to do that. That's perfectly reasonable. That being said, if you're able to predict what's going to happen with some reasonable accuracy, then 16 bits should be more than enough. There's very few recordings these days that get published in 24-bit out to consumers, because there's really very little benefit there, aside from the people who are spending $1,000 per foot for their cables, or something. They probably hear all kinds of things, but or they better, because they spend all the money. If you pay for it, you'll hear it. By the way, that's the other rule of sound. But most things that come out, even the CDs, I mean, that's 16-bit. So the 24 bits really it overcomes our own kind of laziness, or maybe we just want to be safe and not quite push that preamp to the max because we're worried about clipping or whatever. We can be a little lax about that, and it's not going to kill us, right? But if you're doing 16-bit recording and you're lazy with your preamp, yeah, you could have some problems later when you start mixing that stuff. So that's where the 24 bits comes into play. But I've shown you here that 16 bits in a perfect world should be more than sufficient. But it's not always a perfect world. Truth be told, inside the computer's doing a little math that you don't know about. So even if you're operating at 16-bit, the computer's doing all the math at, well, these days, 64 bits. Do you know that? Now you get so the computer, when you say it's a 64-bit CPU or a 32-bit CPU, now they're mostly all 64 bits, even in your phones now. That means that's the size of number that the CPU works with. And any number that it gets sent that's not a 64-bit number gets converted to a 64-bit number first. So that's why all your software had to be recompiled. You can run logic, for example, in 32-bit mode or 62-bit mode. And the difference is how big of a number is it chugging under the hood. So even though you're running it, you've maybe sampled that at 16-bit, you then ask logic to do some stuff to it, EQ it, mix it, add some reverb. It's going to do that at 64-bit resolution.
Is that another form of quantization, or is that not?
What's that?
Is that another form of quantization?
Yeah, sure, absolutely. There's some quantization that happens there. But the theory is that the quantization noise is so quiet at that big of a bit depth that you'll never hear it. That being said, there's this thing called a dither that you can apply to the output. And there are schools of thought as to what you should do with the dither, but let me see if I can explain what's happening here. So in this scenario, like that I've got captured on the screen here, actually it needs to make this work, I need it to be...
D-I-T-H-E-R?
Yep, D-I-T-H-E-R. Let me turn this on and do another capture.
D-I-T-H. Oh, dither.
Dither, yeah. Okay, so here's my 2 bits, right? Well, this is generating some noise, right? And where this really comes into play is on fade-outs, on tails. When you fade something out, it gets right down at the bottom of that bit scale. And what happens is it's alternating maybe between, nothing and something. And sometimes at the end of a tail, that jump can be really big. And that happens anytime you're doing quantization, right? The whole point of quantization is that it's alternating between these two things, and it's really happening somewhere in the middle. And so what can happen with dither is dither actually introduces noise into the signal. Okay? So it introduces this little itty bitty bit of noise. It's like what it's doing is this. And it's just enough noise to cross the bit threshold every now and again. So that instead of this thing that's summing to 0, being quantized down to 0, in fact, so the noise would actually be bigger than this. It would be like this. Okay? So what happens is this thing that would normally be stuck at 0 for that period of time is actually hopping between 0, 1, 0, 1, 0, 1 that whole time. And then that gets fed into your converter, and the converter then converts that and puts the smoothing filter on it, and it smooths out to this great smooth little thing.
And
Technology.
why?
Why? You can say why. That's a very good question, and it took me a long time to figure out why. Why do I care? We're talking about at the bottom end of my 96 dB or 120 dB scale where this thing starts to fall apart. And why? Let me show you. So it has to do with processing. Here we go. This might take a minute to download it. If you can go through this on your own, but this bit depth and dynamic range practical exercise, I have some audio samples, examples of this doing it. What I'm doing is I don't know if I'm going to get it in time because we're almost out of time, but anyway, what happens is, so I have a thing that I've recorded at a very low amplitude and at higher bit depth, and then I fade it out. I do a fade out on it, okay, and then I gain it. I normalize it. So I gain it up. And then suddenly now you can hear the end of that tail where it was falling apart because it didn't have enough bits to work with. And then I have it again where I've done that same thing but with a higher bit depth file. And then you gain it up and it's nowhere near as awful. Well, so instead of going to a higher bit depth, you could introduce dither. And the dither will kind of, it seems completely counterintuitive that you would introduce noise in order to reduce noise. But that's what it does, is it introduces this really very small pattern of noise that causes the sound to kind of fluctuate between bits. And it can reduce the quantization noise as a result, because ultimately when it gets smoothed out, it's less jagged, right? Because it was not sitting at any one of those values for a very long time. It was constantly flipping in between them. And so it averages out to somewhere in between, which is what you were trying to do in the first place. Okay? So if you have your recording that you're mixing at 24-bit, you recorded at 24-bit, you're mixing in a Logic at 24-bit, and then you're going to dump it down to a 16-bit, 48 kilohertz file to play in your show. Well, you may want to apply some dither to that when you do that, because there's going to be some quantization error that results from that 24-bit to 16-bit conversion. And a little bit of dither can help mitigate that noise, right? So you get some of you get not quite all of the benefits of the 24-bit resolution, but you get this sort of halfway point where you're getting something slightly smoother than you would get at 16 bits, without but still at the 16-bit resolution. And so you get this benefit of the lower resolution, therefore the smaller file size. And there's all different kinds of dither, right? So there's the pattern of noise is different. So there's the noise shaping, there's the power dither, these are all different algorithms for people who've come up with the best pattern of noise to put in is this one. And that gets you the best. And we're talking about this little teeny tiny thing that you can't hear. Really, it makes that big of a difference, and people swear it does. But this is all by way of saying there are some people that really suggest that even if you're not doing a conversion, so even, let's say you recorded at 24-bit, you're mixing at 24-bit, and then you're bouncing to 24-bit. Some people say you should still put a 24-bit dither on that, because the computer under the hood is processing that at 64 bits. So it's doing a quantization at the bounce process anyway. So some people really advocate going ahead and putting a 24-bit, because there's different sorts of dither depends on the bit depth. So the pattern of noise for a 16-bit dither would be different than the pattern of noise for 24 bits, because the fluctuation is smaller. So there's some people that say, really, you should go ahead and put a 24-bit dither as the last thing in your signal chain before you bounce, even if you're not bouncing down to a lower bit depth, because the computer's doing it whether you realize it or not. It's doing a quantization. I don't know that I buy that. I mean, maybe, I guess. Again, if I'm lazy with my gain structure and I'm mixing everything really low levels, then I might buy that. But usually, hopefully, if you're doing it right, you've mixed it pretty hot and you've got high levels. So you're not going to notice those differences as apparent. All right. Any last questions? We're out of time.
I gotta ask this.
Yep.
What I hear orchestras in movies that I know do not sound right,
Mm-hmm.
and I know they are live recordings of real orchestras.
Mm-hmm.
Are they dithering? Like what they're doing is they want to put it in the background, like especially in epics.
Yeah.
You know, when you see the crowd, you know, the horses coming, you hear this massive orchestra, but they're really pianissimo. You know, like
Yeah, but it's more that it's not that they're dithering it. What they're doing is they're compressing it.
compressing it.
So they're compressing the dynamic range, because if it gets too dynamic, it can't sit under the scene without being distracting.
Yeah.
So that's what there's. Everything's getting compressed to a 15 to 10 dB dynamic range, and then then they can place it within that scale. So like the music sits here, and the vocal sits here, and the sound effects sit here. So it's compression, which we'll talk about in a few weeks. But, yeah. All right. Anything else? There you go. That's how you teach a computer how to do sound.
Have you heard of Sony's new Walkman?
You are genius. I'm coming.